Thank you, Fabrizio. Thanks for the intro. Also, thanks for inviting me. It's really great to be here. So today I want to talk about some of our recent work on doing near memory hardware acceleration for sparse processing. Actually, for many of these data intensive applications, it's crucial to exploit sparsity, right? Because the gain obviously is huge. With sparsity, we can reduce the amount of data that needs to be processed by often orders of magnitude. And also, for some of these graph applications, we simply cannot get away using dense storage, right? Because of the low density of these non-zeros. But there are also many challenges, right, to enable efficient and fast sparse processing. Because if you look at many of these workload, right, over here I'm just listing some of the common ones, like deep neural nets, right, and also graph learning, graph processing, and these days people are even converting genomics workload to the sparse domain. But if you look at this workload, they are often highly memory bound, and also they have varying degree of sparsity, and also they have unstructured patterns in compute and data accesses. So these are the challenges. But if you look at some of these workload more closely, we do see that many of them actually share some of these common compute kernels, which can be expressed in terms of sparse linear algebra, right? So with that said, actually specifically, if you look at some of these compute kernels, they are often in the form of this sparse matrix dense vector form, often called SpMV, or SpMM, right, which is sparse matrix dense matrix, or SpMSPV or SPGen, which is sparse matrix multiplication, right? These are the some of the common primitives. So with this said, right, given this observation, this motivates us to develop this near memory hardware accelerators to speed up some of these common sparse linear algebra primitives, right? It's also called as motives, right? And specifically, we really want to leverage the bandwidth of the high bandwidth of HBM, right? The high bandwidth memories, because these applications are highly memory bound. And also one of the key things, right? One of the key approaches that we're taking is we want to do the co-design of the sparse storage format and the accelerator architecture. Also, we use HLS a lot, for good reason, right? To enable fast and productive design and prototyping. And we also do many implementations and prototyping on the FPGAs. So these are our key approaches. In the past couple of years, my research group have developed quite a few efficient sparse accelerators. I just want to give you some examples. For example, Tensors is actually some of them are targeting ASIC and some of them are for FPGA. Tensor is one of them that targets ASIC. This is accelerator designed for sparse dense matrix and also tensor operations. This is published at HPC 20. And later at Micro 20, we publish a paper where we look at how to speed up the sparse matrix multiplication, which is basically SPGen, using a non-conventional approach, using the row-wise product, and that turns out to be very efficient. And we are also looking at this also a ASIC targeted project, so where we look at how to leverage many core in this specific case. This is actually a collaboration between UW and Cornell. So where we are looking at how to leverage many RISC-V cores to speed up both dense and sparse tensor processing. We actually have a framework that can go from PyTorch all the way to this many core architecture, and then do end-to-end simulation. More recently, we are looking at how to leverage the HBM-enabled FPGAs. So this is something that I'm going to elaborate on in this talk. So to speed up some of these common sparse primitive and also for graph processing. Okay. This is gonna be the focus of my talk, right? For the remaining presentation, I'm actually gonna mainly talk about two recent work. One is called HiSparse. The other one is called GraphLily. HiSparse is more specialized, is more application specific. This is where we focus on SpMV acceleration, and GraphLily is more of a domain-specific accelerator architecture, where we also use the linear algebra formulation to speed up graph processing. Okay. So let me start with HiSparse. This work was recently presented at FPGA 22, actually just a couple of weeks ago. This is a joint work with my student Yixiao and Yue. Like I mentioned, we use HPC a lot, right? The source code of HiSparse is already open source. This is all written in HOS, so feel free to check it out. The reason we are interested in looking at SpMV is because first, this is one of the most commonly used sparse primitives, right? It's used in many different applications. Again, SpMV means sparse matrix times dense vector. Okay? And also it actually shows many interesting and common characteristics, basically a good representative to study, good case study. If you look at SpMV, right? First, let me just fill it out, right, with some elements, right, some non-zeros in the sparse matrix, and we assume the B vector to be dense. If we look at the compute over here, we can immediately tell that it has this low compute to memory access ratio or low operational intensity. For example, over here, if you look at the calculation of C1, we actually only do 2 arithmetic operation, right, multiply, add, but with multiple, right, actually 4 memory accesses. And also we have low data reuse, right? In this case, if you look at the non-zeros of A, right, in this case, for each one non-zero, we only use it once, okay? Which is also bad for this operational intensity. In addition, if you look at the access patterns of the dense vector, we're actually doing a random access, right? Which makes the memory access pattern unstructured, irregular. And also we have the so-called carried read after write dependencies, right? For this computation, you look at the calculation for C5, we need to sum up the partial product, right? We are doing dot product, we have these strong carry dependencies, which is also challenging, right, for parallelization. So with all of these characteristics, this really makes the SpMV an interesting, also representative case to study. And this is a highly memory bound, specifically highly memory bandwidth bound application. There are actually quite a few prior efforts looking at how to speed up SpMV on the FPGAs. But most of this work target systems that use low bandwidth DDRs. And I just list a few of these. Later on, I'm going to show a comparison against some of this work. For our project, we are interested in using some of the more recent HBM-enabled FPGAs. So these FPGA often use this multi-die integration. The nice thing with this platform is that we have access to high bandwidth memory HBMs. For the specific platform that we are using, the AMD Xilinx Alveo 280 U280 platform, we can access up to 32 channels, right, with this much of a memory bandwidth, right, between the accelerator, FPGA accelerator, and the option memory. So this is actually extremely useful, right, for sparse workload. So these are the nice things, right? We have much higher bandwidth available, and but the challenge really is, right, so how do we make the good use of this bandwidth, right, and to avoid channel conflicts, because this is really the key to achieve high performance, also high efficiency. And also later on, I also mentioned some of the other challenges that's introduced by this sort of a heterogeneous multi-die FPGA that actually cause some interesting physical design and layout challenges, especially from the HOS design. All right. Like I said, right, so one of the name of the game here is to maximize utilization of the memory bandwidth. So that's where we want to look at whether some of these conventional and most popular sparse storage format, sparse matrix format, whether they are suitable or not, right, for exploiting this memory bandwidth. And turns out not quite, right? For example, if you look at CSR, compressed sparse row matrix format, this is one of the most commonly used format. It's fairly condensed. Right? We are using the row pointers over here, right? So basically, this is data structure. We have an array of non-zero entries, and we use the row pointers, right, to do the compression. And for each non-zero entry, we also have the column index, right? For sequential CPU execution, this kind of format is actually not that bad. we do have the non-contiguous, actually the contiguous, right? The contiguous memory access for each row, right? If you look at these non-zeros. But the moment we think about parallelization, also the moment we think about accessing this kind of a HBM memory, things are different, right? Let's say I want to parallelize. I have two processing engines or two processing elements, PE1, PE2, and I want to parallelize right across the rows when I do the SpMV execution. So that's where we can immediately tell that the moment we do this first, because of this row pointer array, we may have non-contiguous, right, non-streamable access to the HBM. So when we have to do this indirect memory access, right? So we have to do get the row pointer and then fetch the data element. And also, if you look across PEs, right, over here, we may want to access A13 and A24 at the same time. But with the conventional format like CSR, we may end up with a channel conflict, which is bad for bandwidth utilization. So this is where we are investigating, different kind of accelerator-friendly, also HBM-friendly sparse format. One of them introduced in our paper is called CPSR, channel cyclic pack format. This is where we partition or arrange the row in sort of cyclic interleave formats to consider the row-based parallelization. And also we remove the row pointers. Instead, we insert this next row marker. So this is really a trade-off between sort of the storage efficiency and the access regularity. And turns out this trade-off, right, at least in our case, is in favor of our accelerator. So if you look at this kind of a format, right, we are having streaming or vectorizable access when we look at the data access. And also when we parallelize across rows, we are guaranteed not to have channel conflicts. Okay. There are other formats that we're looking at. Actually, this is a very interesting trade-off space. This is something that I can talk more offline if you're interested. Just want to quickly show you the overall architecture. We organize these compute engines or PEs in clusters. Each cluster directly connect to HBM channel. Of course, we want to use many HBM channels, right? And also we put a number of PEs per cluster. So this is where we do vectorization. So we also want to read out the entire vector per cycle from each channel to really maximize the bandwidth efficiency. And inside each cluster, we also have a buffer, on-chip buffer for the input vector, and also we have the buffer for storing the intermediate result and also the final results. Okay. So this is the overall architecture. I'm gonna give you more details later on. And speaking of these on-chip buffers for the vectors, actually there's also some interesting trade-off because if you look at FPGA, actually in general for accelerators, right, we are still limited in terms of the amount of storage we have for on-chip SRAM. We can, since we are doing parallelization, we can choose to, just use one big buffer to store the dense vector, but that's gonna incur a lot of, access conflict. We can also choose the other extreme option to duplicate everything, right? Duplicate the dense vector for each PE, but that's gonna be too much of an overhead, right? We don't have that much of SRAM. So that's where, we have to sort of find, to make a compromise, right? So that's where we use this shared dense vector scheme. So basically, we use the bank memory. So we do duplicate, but we limit the degree of duplication. And we do share the dense vector for a number of P's. Right? So this number is configurable. So that's where we have a more efficient use of on-chip memory. But obviously we have to handle the bank conflict, right? The bank conflict may occur, although the goal here is to minimize the occurrences of these conflicts. So that's where we have to insert a shuffle unit to manage the data request and also the bank conflicts. And this shuffle unit is actually not that trivial to design in HOS. So I'm just showing some of the simple code snippet here. If you just do a simple loopy code in HOS, HRS will assume, of course, HRS is doing this static offline analysis. We'll assume the worst case traffic pattern, and this final throughput is going to be pretty awful. So that's where we have to actually specifically design, a shuffle unit in HRS. We have to design this, routing arbitration logic in the lower level using the more low-level code. Okay, I'm not going to get into detail here. So this actually opens up. I personally think that it actually opens up many research opportunity for better HRS tools. So especially for this to handle this kind of sparse processing. Also, the other challenge for HRS is how do we handle this kind of a sort of dynamic, less regular carrier dependencies. Again, using a microprocessor, we do the data forwarding, to handle this dynamic data hazard. But with HOS, since all the pipeline registers are automatically generated by the tool, they are actually not visible at the source level. That also caused some challenge for handling these data forwarding. So again, in this case, we have to design a dedicated data structure called in-flight write queue. So to manage the data forwarding explicitly at the HOS level. Again, if you're interested, just check out our code. This actually provides some good templates, because these days there are many good HRS code templates, for handling sparse workloads, dense workload, like matrix multiplication, how to do system arrays, how to do line buffers or window buffers for extensive processing and such, right? But there are actually not many useful templates for handling this kind of sparse processing. Okay, so this is the architecture again. Right, like I mentioned, we implement everything on Alveo U280 FPGA. We end up using 16 channels, although there are 32 available. I'm going to briefly mention why that's the case. Okay, and for the sparse matrix, and we use 2 additional channels for the input and result vector. We end up using this amount of total bandwidth, to 58, which is pretty decent. Although we do want to use higher bandwidth later on. And we are using quite a bit of on-chip SRAM to store the result and also the vectors. Okay, and actually, all of this we do have a systematic way to search these design space to decide, how much buffer that we need. So more detail are in the paper. Okay, and this is the resource usage and also frequency. We are able to reach to closer to 40 megahertz. But with a caveat, so we have to use floor planning. I'm going to mention this also. And you can see that if you look at the actual resource usage, for sparse processing, it's really, a memory intensive, we are not using all the on-chip resources for compute, but we do need a lot of resources for the on-chip buffering, especially ERAM in this case. Okay, just want to quickly show you some results comparing to CPU and GPU baselines. We actually evaluate a number of different data sets. We evaluate some of the more dense data sets. These are the transformer data set, and also some much more sparse data sets. These are graph data sets. So across the board, we are actually doing much better than CPU, in terms of performance. We are on average 4x faster than the highly optimized Intel MKL library. And we achieved similar performance with cuSparse, nearly the same, in terms of throughput, in terms of GOPS. Okay, I'm actually pretty excited about this result. I'm going to show you later. We can get even better, and I do believe that we have additional room. But this is the performance. How about efficiency? Oh, by the way, I want to quickly mention, so we are doing multi-threaded execution, for Intel CPU as well, and Intel CPU has access to a similar bandwidth, I do have the comparison on bandwidth efficiency. Again, we are doing better than both CPU and GPU, so we are using the bandwidth in a much more efficient way than Intel CPU using MKL, and also the NVIDIA GPU using cuSparse library. With cuSparse, with this specific GPU, it actually has access to a much higher bandwidth. And also we do measure, so this is not TDP, we do measure power using the utilities from different vendors. So this is the actual power. This is the the sort of the power of the card. And in terms of the energy efficiency, right, FPGA obviously is also in this case doing better than both CPU and GPU. Okay, and also we compare with some of the recent work on FPGAs. Right? We compare with some of the GP. This is a very recent work, although they are currently targeting DDR. Right? In this case, we are getting higher throughput. Okay, and also we compare with Xilinx, this commercial library, Sparse library. For this library, they currently cannot support large matrices beyond this size. Okay, so that's why we limit ourselves to some of the smaller matrices, but we are still doing better than a commercial library. Okay. Also want to quickly show you some more recent result. So that's where we actually managed to scale up to more channels. Okay, I just showed that we can scale to 16 channels, but with the most recent result, we can get additional speed up with additional channels, which is actually not surprising, but we're actually pretty encouraged by this speed up, because our goal eventually is to speed up to get even higher speed up, to scale up to even more channels. On that platform, we have 32 channels, but right now we are running into some routing congestion, so this is something I'm going to mention. All right, so this is HiSparse, right? Like I mentioned, this is a more application-specific, algorithm-specific accelerator as implemented on FPGA. Let me quickly switch gear and also briefly describe GraphLily. This is a domain-specific accelerator. And GraphLily and HiSparse, they are connected. Although I just want to quickly point out that GraphLily was published earlier than HiSparse. Some of the the SpMV accelerator, the most recent SpMV accelerator in HiSparse was not incorporated in the GraphLily yet. So that's why you will see some discrepancy in the results. Okay, so like HiSparse, GraphLily is also written in HOS. It's fully open source. Okay, this is published at ICCAD last year. Joint work with my student Yue, Yixiao, and Edgy. So GraphLily is really about speeding up graph processing on FPGA. Again, there are a number of prior studies doing graph acceleration on FPGAs. But the key difference here is that all the existing work so far, so they target the specific algorithm, graph algorithm, either BFS, breadth first search, shortest path, or PageRank, or others. But the problem is that, if that's the case, we actually need a separate bit stream, for different graph algorithm. We all know that generating a new bit stream, especially on a large FPGA, is very time consuming, can easily take 10 hours, 20 hours, or even days in some cases. And even if we pre-generate this bit stream and store it somewhere else, and then do the dynamic reconfiguration, the runtime reconfiguration cost may not be that trivial, It's either in the order of milliseconds. Okay. So these are the downsides, Ideally, we really want to have a more, programmable, more configurable, and more versatile, multi-purpose accelerator on the FPGA that can handle many different kind of graph algorithms. That would be an ideal case. So this is where we investigate. So this is where we are looking at how to leverage this so-called graph linear algebra formulation, to enable a so-called FPGA overlay, to handle multiple graph algorithms without generating additional bit stream. So this is what we have so far. It's got GraphLily. I'm quickly showing you the overall sort of system stack. Again, we are leveraging the HBM equipped FPGAs. With GraphLily, we are using this linear algebra formulation again. We have this set of sparse accelerators, SpMV and this SpMV. I'm going to quickly mention this, and also some of the element-wise kernels. We can support multiple different kind of algorithms, BFS, PageRank, SSP, shortest path, and we also provide the middleware. So user can directly use the GraphBLAS like programming interface and directly program the FPGA. Okay, it just take seconds, instead of hours to program FPGA. Also, it's easy to port existing GraphBLAS algorithm from CPU, GPU implementation to FPGA. Okay, so this is probably in a nutshell. So in case you're not familiar with graph linear algebra, I should not give you a quick intro, right? I'm pretty sure most of you are familiar with BFS, right? This is a graph level view. We start with certain frontier. In this case, frontiers B and D, and then the next frontier, right, with BFS can be the green nodes, right, C, E, F, H. So this is the graph level view, and turns out that we can also express it using the language of a linear algebra. Over here we are using the adjacency matrix of the graph, and then we express the frontier using a vector. So by doing this, SpMV, right, in this case, really the graph adjacency matrix is sparse. So by doing this matrix vector multiplication, we actually get the new frontier also in a vector form. So that's basically how we convert a graph level traversal into linear algebra operations. Okay, of course, in many cases, right, this frontier may not be dense, right? So this frontier might be pretty sparse. So that's where we have a trade-off between using either SpMV, right, sparse dense multiplication, or sparse or SPM SPV. Okay, with SPM SPV, we don't need to do dot product. So we just have to do a scalar. We express the frontier using sparse format as well. We just need to use the scalar vector product. There are some interesting trade-off, which is something that I'm not going to elaborate too much. With SpMV, we have more work. SpMV less work. But SpMV is easier to parallelize, and SPM-SV is slightly more challenging. But I just want to quickly point out that for many of you who are familiar with graph processing, right, on CPU, GPU, there's something called pull-based and push-based, right? So this is basically the sort of counterpart, right? So pull, push, and there's a way to determine when do we use SpMV and SPV by looking at basically how sparse is the frontier set. So this is actually the so-called a well-known direction optimizing heuristic initially proposed by Scott Bittmer for BFS acceleration. Okay, a little bit more about GraphBLAS. Like I said, right, GraphBLAS wants to express this complex graph algorithms in terms of sparse linear algebra, but in a more generalized form. Okay, so in the sense that we are not just limited to doing the multiplication and addition on floating point data types or integer data types. So instead, we formulate these operations over this algebraic structure, segment rings. We can have arithmetic segment rings, so that's where we have page rank. We can also instead of using a multiplication, we can use AND and OR. So that's where we have this Boolean segment ring to handle BFS, and so tropical segment ring to handle shortest path. It can actually handle a pretty extensive list of interesting and common graph algorithm using this formulation. There are some implementation targeting CPU and GPU, right, for GraphBLAS, and GraphLily is really the first work on FPGA. Okay. And also in terms of the programming interface, like I said, right, it's relatively easy to port. The GraphBLAS or GraphBLAST. GraphBLAST is really for GPUs. We just need to insert a few lines of code to basically specify the bit string and the matrix, and then we just run it. Okay, as simple as that. Okay, so just want to quickly show you some results. This is also running on Alveo 280. In this case, we are using 19 channels. But like I mentioned, right, so this is earlier work. So back then, we were only able to achieve 165 megahertz due to many physical layout problems. We are integrating with HiSparse. GraphLily is actually using a less efficient and less optimized SpMV accelerator. Okay, but still, in terms of resource efficiency, it's actually pretty good. So if you look at the overlay, right, so GraphLily is really overlay. It can handle multiple different kind of algorithms. But if you just look at the resource usage, if you only implement a BFS specific accelerator versus a multi-purpose accelerator, an overlay, if you look at the difference in terms of resource usage, right, actually not much difference, right? So hopefully this convinces you that, we are indeed doing a lot of resource sharing across, different applications. The reason that we were not able to achieve a high frequency is because on these kind of multi-die HBM enabled FPGAs, there could be a lot of congestions right down here in one of the SLRs or dies. because of the these memory controllers are really sort of they are located together, which is not ideal. So there's a lot of congestions that prevents it from using more channels. And also with this multi-die, the die crossing signals, they are typically pretty slow. So in some cases, if we cannot avoid that, then the frequency drops quite a bit. We do have some other work to address these kind of challenges, right? If you're interested, I am more than happy to discuss. Okay, so again, some results, right? Comparing to GraphIt, right? So one of the more recent and popular framework, right, for graph processing on CPUs. With GraphLily, we can get 2.5x speed up, and compared to GraphBLAS, right? Also, graph linear algebra formulation, we also get higher performance on GPU. This is PageRank. There are more results on BFS and shortest path. Right? Feel free to check out the paper. And we have results comparing with other single-purpose accelerators as well. So that's where we get the good news is that we are actually more performant, and also we don't have this overhead of reconfiguration. All right, so just want to quickly conclude. Right, this is I talk about, right, so near memory graph processing, right, near memory acceleration of linear algebra. So I really think that this near memory hardware specialization is a promising way for specialized, efficient and fast sparse processing, because we have specialized memory hierarchy and data layout that really enables us to get the high memory bandwidth utilization. Really, that's the key to improve efficiency. And also HPC and FPGA is a very good platform, right, to do some of these experiments with the two examples, which hopefully can be used as useful references for the community. And there are still many interesting challenges, right? Like I mentioned, HOS for this kind of bandwidth demanding accelerators, and how we can further increase the programmability without hurting too much efficiency, and also how can we handle end-to-end acceleration from even higher level program like DSL. So these are some of the things that we're working on, and I'll be happy to chat. Okay, with that, I'm going to stop here. So I just want to show you the link again, right? So these are open source, right? Feel free to check it out. Thanks for listening.
Thank you very much, Zhiru, for the presentation. It's very interesting.